Morning. So we're going to go
Good
through.
morning.
Hmm. We're going to go through the last week's week 12 questions, in which there are more focus on not just decoder based network but encoder decoder combined. Okay, and they can be applied to a variety of problems as shown in the lectures, and further how attention can be applied to such networks, and also in vision system to have visual cues over the whole image, because in CNNs the dependence between pixels is only local, okay, not global. So how to give it global interdependence is through attention in vision. Okay, that is what we're going to see. Okay, so we're going to solve few questions in that as well, and this is the agenda for today.
Sir, I have not got my hall ticket yet. What is the reason for that? When can I get it?
Well,
The
I'm
exam is on 17th.
so they say uh, first means like within a week, like, but it is already post that, right? But I'm not actually concerned person in that. Actually, I'm just only for teaching work here. Logistics for
Okay,
exams is
okay,
not controlled by me actually.
okay, okay.
So I can give you an email where you can contact.
Yes, sir. Yes, sir. Please give. Good.
Okay, so let's get started. the other questions we have to do? Visible?
Yes, sir. Yes.
Okay. So a translation system without attention, so there is no attention mechanism, translates French sentence into English. However, it often produces incomplete or grammatically incorrect translation for long sentences. Okay. Which issue is the sequence to sequence model does this most likely illustrate? So these are the questions. Okay. So how are we going to do it? So first let's understand how a sequence to sequence model in this case is designed. Okay. So this is the RNN. Okay, so this is the encoder model I'm going to write. Okay, so the French sentence, each words is like input like this into the rollouts of the RNN. Okay, and the hidden states of this is calculated, right? So this is from S0, then S1, S2, S3, ST. Okay, now this ST is fed to this. Okay, another, let's say HT, it will decode now. HT minus 1, like that, to H0, and it will produce the output English words. Okay, this is the structure. This part is the encoder one, this is the decoder one. As you can see, taking the context here, the hidden representation is, it starts decoding. Okay, this is the structure of the encoder decoder model. Okay, now which problem is it suffering from? Okay, so the problem is, here you can see it produces incomplete or grammatically incorrect translations for long sentences. Focus is on long sentences. The sentence is long, it produces incomplete. Okay, it cannot produce the full sentence that is desired, and also grammatically incorrect sentences. So the grammar it cannot properly understand. Okay, and you can understand the grammar actually depends on all the words in the sentence. If it is not able to capture all the words in a long sequence, that's the problem it is having. Okay, so what is happening, it is unable to capture long context in a long sentence, context specifically of the initial words. Okay, so this is the problem it is having. Okay, and so limited size of the vocabulary, is it a problem? No. Why? The vocabulary is smaller, then it is actually easier for the model to do it. Okay, but it can happen that vocabulary is too much restrictive, and that is why it does not have the information. But usually for long sentences, okay. Hello, you're saying something? Huh? Okay. Another is like overfitting to training data. Okay, so if it overfits, okay, then it not be, if it overfits, then not be able to produce good results. Okay, but the focus, as you can see, is on long sentences. The problem is it with long sentences. If it is short sentences, there is no problem actually. Now the context vector that it is learning. Okay, the so what is happening in that, if the context vector, so as you can see, context vector is capturing the information. If the context vector is too short, okay, so there is more information, more compressed information cannot be captured. Okay, so losing information due to that. Okay, so that is the answer here. Okay, Incorrect tokenization. Incorrect tokenization will be problem in short sentences as well. Okay. Overfitting will be for problem in short sentences as well. While long sentences. Okay. Let's see the size of vocabulary. Okay. So if the limited size of vocabulary is there, and suppose the words are like out of the vocabulary, okay, that will be problem in short sentences as well. Okay. So this is what we're having. Okay. So these problems are for short sentences as well. This is only for the long case we're having. Okay. Any doubt in this? Why I did it like this? Any doubt?
No, sir. No, sir. No, no, no.
Which of the following are valid motivation for introducing attention in sequence to sequence model to capture the context better? Okay, long context. Okay, so this is basically the answer.
Sir, here context means meaning of the sentence, like the internal meaning of the sentence means context, no?
Yes, yes. So, so let me. Hmm. So let me explain how the things exactly happen with attention here. Okay. So so attention. Just to give you a better detail, there are two types. One is a dot product based, which is the modern attention today, and another is the softmax based. Okay.
Sir, in transformers, we are using softmax based transformation attention, right, sir?
The dot product actually, because you need to do the dot product of the two embedding matrices to calculate the to calculate the attention. So you will see here. So this is the paper actually where they do it differently. So this was the first attention given in neural transmission.
Sir, that heading can you show so that we can capture it?
Yes.
No, the title, sir, title.
This is
Title.
title.
Just 1 second, sir.
Okay.
Yes, sir, we captured it.
I think this paper came after the course video recordings. That is why it is not in your. Let me display. So I think the course name of the answer. Okay. So what was I saying? So this is a paper. This is first introduced attention as a concept in neural transmission. So let's focus on the problem statement first. Okay. So you'll understand very well what is being taught here. Okay. So this is our RNN, right? Uh,
Yes.
Let me show the downloading. So, so as you can see, this is a so we are using an encoder decoder framework for neural transmission. Okay, encoder reads the input sentence and a sequence of vectors. Okay, so what is it is doing? It is preparing a context vector C by reading the input sentence, which is described like this. Most common approach is to use RNN such that this every hidden representing this is the context vector what we have seen. So what is the context vector here? It is so Q is a neural network, okay, feed forward neural network here, okay, and it is fed every hidden representation at every time step, okay. So in the LSTM represent in LSTM what do you call implementation is the most popular of RNN because of its like non-complex capturing ability. Okay, the what you call that vanishing gradient problem is not there in LSTM. Okay, that is the main reason of using LSTM. Okay, so LSTM is F. Okay, and like from Q non-linear functions is neural network. Okay, feed forward one. Now F is not feed forward. F it's the recurrent neural network. Q is the feed forward one. So LSTM is F. Okay, easy to understand. And so what they do here, they do not take the uh, full all the hidden representation, but they say that the last hidden representation captures all the information. So that it is the context vector they want to say. Okay, so so this is what practically done. Basically, network is usually not trained. Okay, they just take the last hidden representation as a context vector. Okay, for the decoding. Done. Now the objective of the decoder, how decoder is done. Okay, so the mathematical objective as we have seen in the lectures as well. The context vector C, which is ht, what it will be here. Okay, and the words occurring before that. Okay, we want to calculate the probability of occurrence of this token. Okay, and over all the time sequence, it is the product will be there. Okay, okay. In other words, the coordinate defines probability over the translation y by decomposition the translation into order conditional. Okay, so this is the objective of the decoder. Any doubt in this?
Sir, the decoder functionality, I could not understand what it is doing. Like in the encoder part, it is capturing the initial context, the whole context at the last hidden layer.
So,
And decoder, what it is doing?
so it takes the context C, which is ht or can be like q of h1 to ht,
Okay.
like that,
Uh-huh.
and this uh, what it does, it produces first y0 or y1 y1.
Mm-hmm.
So there is no input here in this case. Okay, so context and y1 is the input. And for the next one, it gets, so this is uh, t, ht is the information. Okay, uh, and this one is ht minus 1 by 0. Okay, and it produces y2. Input is here y1. So the what output here is taken as input here, and like that it is represented until the end of the simulation. Okay, so that is what is shown in the this probability as well. That every so here you have to understand this, the h t that is passed, okay, captures y1 to yt minus 2. Okay, so this becomes p by t equals ht minus 1 and yt minus 1. Okay, and the context is given to only the first this one first iteration of the RNN. Afterwards, this ht minus 1 word acts as the context. So this is the simplification, you can say.
Okay.
And so what you can see, the decoder defines probability over the translation while the decomposition non-probability to order condition. So it is doing, understand this. So it has to calculate the probability of this given. So this is
Probability of other context. Okay.
no no so this is the like this probability, okay, has to be. So this is the output of the decoder, okay, and suppose the uh, so output, let's say by dash, and the input by y1 y2 y3. This this joint probability has to be maximized. So what it means is that input sentence is this and output is this, and this probability has to be maximized. Okay, if they are same, okay, close to one at least, like that. Okay, so now by Bayes theorem, what we can write, this can be joint distribution written as the product of prior times condition. Okay, so how do we do it? So given P1 probability, this becomes P y2 zx, okay, like that, and like that continuously. Okay, you understand? So this are constant, okay, so this becomes
Hmm.
the conditional become product.
Mm-hmm.
So that is what they have written. The joint probability can be written as the product of conditional probability. So this is what they have written as well. Okay, simplification. And now the attention part comes. So this is description of the RNN, encode decoding attention. Now, now we have to see. So this is the encoder structure, okay, and this is the decoder one, okay, and
Mm-hmm.
they use a bidirectional RNN for encoder and single direction for decoder. Okay, so this is the structure we have. So what the question we were having is uh, motivation for introducing attention. Okay, so let's do this question first, then we'll see the problem. Okay, uh, so you've understood the structure of the RNN for sequence to sequence translation. Okay, so this structure was defined before this paper actually, like in the preceding paper. So in the introduction section they have written that in the content of the paper is on attention actually. It's saying improves perform this over long sequences. Okay, so now which of the following are valid motivation for introducing attention in sequence to sequence model? To allow decoder to dynamically select relevant encoder input outputs for each output time step. So this is important. Okay, so attention decides, like without attention what happens is that the inputs which are closer to the sentence are given more importance. Okay, but attention allows the model to learn which input has to be given more importance while producing the decoder's output. Okay, the attention decides that, maybe in the middle, maybe in the third position, maybe the first word is more important, maybe the second last is most important. You, if without attention what happens, you're taking the nearest words to be most important, but maybe the farther word is more important actually. So this is the problem. Okay, to complete the need to completely remove the need for an encoder, so encoder is still required to produce the context vector that is needed. Okay, and the context vectors now is, like we'll see, will be like encoder is still there, but encoder will help to calculate the attention, and attention will finally decide the context vector. Okay, so but encoder will still be required to overcome the bottleneck of fixed length context vector. So this is also important one. Okay, if it is too short, you lose information. To ensure that the model encodes ignores irrelevant tokens in the input sentence. So irrelevant tokens which are like suppose is and like those things, filler words are, okay, those don't add any value, but their representation is also given equal value. That is a problem with attention, you can ignore them. Okay, so let's come back here again. uh, so this is the so it is again describing the decoder here. As you can see, we define the so in the new model architecture, the architecture they're proposing, each conditional probability in equation 2 as this. So the decoder can be written as this. We have seen that as already. Okay, SI is the RNN hidden state for time I computed by this. Okay, so this is the one. It should be okay. So let's understand here. I think they have defined G as the decoder and F as the encoder, right? So we have to see that here. Okay, so what it is telling is that this SI are this hidden states. Okay, hidden state for each uh, encoder. Okay, in each decoder time step. Okay, is calculated like this from the encoder itself. Okay, so the encoders so encoder takes the so you have to see that. Let me draw. Okay, so how they have explained is a little different. Okay, to what lectures or what I have explained. Okay, so the hidden states of encoder, okay, is actually this is hidden state for the decoder as well. Okay, so that is what how they explain. Okay, let me show you. So suppose we start with S0 here, then S1 is created, S2 is created, T minus 1 is created, ST is created. Clear? Now what we are having is this S1 is calculated like this. Okay, and yi minus 1. Hmm. It is little wrong here. I mean, the encoder only takes the x values actually, as you have seen here actually, xt and ht minus 1. They have done some mistake here. Let's ignore that. Okay, but maybe it is not important. Okay, so si are the hidden state of the decoder, and as you can see in the definition here, ht are the hidden state of the encoders. Okay, so that is how it is. Okay, let's not confuse. Okay, let's ignore this line. Okay, here the probability is conditioned on a distant context vector is seen and target word yi. Context vector c depends on the sequence of annotation. This we've already seen that. Okay, so how now they so previously what you have seen, the context vector was taken as this ht, or a mlp was used to learn a context vector over all the hidden states. Okay, now they are saying we'll use you will learn this context vector in a different way. How? It will learn over a sum over weighted sum over all the hidden hi. Okay, and the weight is this alpha ij, which is actually the attention scores. Okay, now this alpha ij, which is the attention, is calculated using a softmax way, exponential of the required one divided by sum of exponential of all the ones. Okay, so this is softmax structure, right? Okay, so what they are doing, they have written that this energy, okay, energy. So so energy notation is from physics, okay. So the understanding is this E to the power uh,
Sir, in exams also they are asking these symbols like write the formula, but but how we will write these symbols sigma eta in that exam platform?
they will
That
not
is
ask formula
challenging,
like that.
no?
There will be options to choose, okay. You have to click on that.
Okay, okay.
Okay, so this is called energy, which is defined as the MLP learning over Si minus 1. So Si minus 1 the hidden states of the previous hidden state of the decoder RNN, and Hj is the hidden state of that input hidden. Okay, so what you're saying is, so I need to calculate, okay, so attention alpha ij, okay, I need to do this calculation, okay. So j is actually the variable here, okay, okay. And so the calculation, as you can see, is so it takes the previous, so attention for this time step we're calculating, okay. We're calculating, I mean the context vector for this time step. So this is, let's say, ct, okay. So in that you will see that the summation is over j equal to I 1 to t, and j is on the, so it takes the hidden representation of the input, takes consideration of all of them, okay, to calculate the context vector for this, okay. So all the hidden representations are important, so because they're summed over, okay. So before sum you'll focus on one hidden representation. Let's say this alpha. So for that, and for that each hidden representation we need a alpha, okay. So we focus on alpha t2, okay. So t is from here, and the second position I'm taking, okay. So if I have to calculate alpha t2 here, so let's see here. So that I is here fixed, right? I is t here, okay. I is fixed, only the 2 is varying, okay. So j is 2 here, okay. And this 2 is represented dependent on this h2 here. So h2 is the important thing, okay. And si minus 1, si minus 1 is this one. So it takes this hidden representation of the previous step of the decoder RNN. It moved away somehow, okay. and and the hidden representation this, okay, to calculate this alpha t2, okay. And similarly for a fixed st minus 1, this all these are taken into account, and this eij values are calculated, okay. eij values correspond to an alpha ij value, okay, and these are summed over to get the context, okay. So this is the improved context, and you can see here the difference between earlier what we were having, we're just taking the final hidden state as the context or MLP over it. So the model does not know which hidden input hidden representation to be more important over, okay, which is more important we don't know. But here which hidden representation is more important is decided by this alpha, which is the attention, okay. If it is more, alpha is more, then the importance of this hidden representation is more, okay. So this is the difference, okay. And model gets to choose which hidden representation alpha needs to be more from this neural network, okay. And how it does that? So it calculates this eij, which actually decides alpha ij value, okay. This is a just normalization, okay, just so that it is the sum over alpha ij is 1, okay, over 3.
So like it depends upon the probability. What is the probability more? That only have more attention. That only they are
But
telling.
how are you understanding probabilities from this? don't know. So it is comparing, it is
Mm.
understanding the relation between the hidden
Mm-hmm.
context up to this point, okay,
Mm-hmm.
and the
Mm-hmm.
context captured in this, okay. So what does this hidden representation capture? It captures the context of the output sequence up to yt minus 1, right? So it captures that information, okay, clear? And now this is the information captured. This hidden representation captures the information for input sequences up to x2, clear? So
Mm.
suppose uh, just some sequence, I don't know, let's say like 1 2 2 3, okay, up to two steps and x and y, okay, like that. This is a sequence we are having, okay. It does not have any meaning. I could have given a better example maybe, but I don't know to make languages, okay. So so what will happen? So here, when we're calculating attention score, so here we have st. So this, let's say this is the st minus 1, and there is another one digits here, which is st here, okay. So up to this point it's st minus 1. This is calculating information how these interact, okay, and then calculating the context, okay. Now, so now this is like, so this is z like that. Suppose I take this one. This is the ht here, h2 here, or ht, what you will say, okay. So it is understanding how y, okay, upon the input, just this input, okay. This is not considered, okay. Is it considered? It is considered because the hidden representation also take the hidden representation of this we will calculate, okay. So up to how these two, how part of this sentence actually interact with each other, okay, how structure of the input decides the output here, okay. So that way, okay, it captures the dependence between each other, and that results in the context vector here, okay. And we will also do it like this, as you can see, that h, so for every h it is calculated, right? For up to this it is calculated how this part is decides this sentence, okay. How two of these decides this sentence, how three of these decides this sentence, okay. So like this all combination there, it will be able to decide which part of the sentence is actually important for decide the decoded sentence, okay. Understood? So in this way it is able
Yes,
to
sir.
capture which is the most important section of the input sentence, which decides the output sentence up to a time step t. Okay, previously what we are having, the closest ones are giving more
Mm-hmm.
information, okay.
Yeah. Surrounding sentences.
Yes. So that was the problem we're having. So attention solve that, and which part of the sentence is important, which one we know, okay. So
Mm-hmm.
let's see again. Irrelevant token, suppose is a are, these are irrelevant, there is no meaning in it, okay. So attention score
Mm.
for these will be very low,
Yes, yes.
okay. And bottleneck of fixed length context vector, okay. So context vector is still fixed length, but what we are having, the information is better stored. If this irrelevant information is deleted, so there's space for better information, okay.
Mm-hmm.
So it dynamically selects relevant encoder outputs, okay, for each output time steps. So which is the more relevant encoder output? So it is able to dynamically select that one. This is how it is. Understood?
Mm.
So this is the problem we have. Okay. Hope I made it very clear. You can check out the paper again. Paper is not too hard.
This paper they have given in reference. I did not check it.
I don't know.
transformers.
Model parameters. Yes, transformers. Able to see? Or is too small?
Yes, sir. It's too small. Previous one was okay. Was able to read.
In English to German translation, so this is the what we're having. Is observed to generate German tokens, okay, as this with the correct word order. Okay, so it is working correctly. Attention weight visualization shows high weight between cake and kuchen. Between 8 and this. What does this indicate? Okay. So if high weight is there, attention weight is high. This means that these two words corresponds well with each other. Okay, so maybe they are the same word actually. Cake means kuchen only, and 8 means this. Maybe like that. I'm not sure. What does it indicate? Attention ensures perfect translation without a need for training. It doesn't work like that. We need to train the model first. Clear? Okay, this paper is there. Yes. You have in your attention. So it is in the course as well. Okay, you have to study that. How is the alignment score between the encoder state HI and decoder state ST is typically computed? Okay, so how the alignment score is calculated using a MLP, feed for neural network with trainable parameters, right? Done. You have seen this. Okay, let me show you again. So this is what it is referring to. This is the most important line. You get EIJ, then you get alpha IJ due to softmax. Okay, you get alpha IJ. This is the sum. This is the weighted combination. You get context vector CI. So done this one. Okay, so next question is sequence to sequence model generating weather report from satellite data. At decoding step T, the model calculates scores between the decoder current states and each encoder hidden state. Then applies a softmax to obtain weights. So we have seen all this. Okay, what is purpose of these weights? Okay, so weights are the attention weights. So what does the attention do? You have to see. Okay, decide the vocabulary size wrong. Determine how much encoder hidden state contributes to the this is the right answer. Okay, we have seen this already. Initialize the decoder hidden state for the next. So initialization can be done by the decoder itself. To normalize the encoder output have zero mean, that's wrong as well. Okay, clear? No doubt. To read the Bahadanu paper, so it is too easy.
So the paper you shared now, that is part of the paper. That
Yes.
one you are telling.
Hmm.
Okay.
What happens after the attention weights are computed in additive attention? Okay. Additive.
Excuse me, sir.
What are you saying?
Hello.
Yes.
Hello. Sir, one thing I need to clear about that in the screen calculator, whichever you have sent, the corresponding exponential value, like only we can calculate like e to the power one. Rather, we cannot calculate e to the power 1.5 or e to the power 2. So in that case, how to do this?
Mm,
In case exponential of 2 comes, then how to calculate using the screen calculator? Because it does not take E2, only it takes E1. It gives the value of E1.
e to the power 2 not possible.
Yes. No?
Okay, then you have to take if you calculate e value, I think it is like 1.7 or something. And you take the power, then you
That
get the
is,
power you want.
okay. First, we have to take e to the power 1. Then, after that,
Then if this is the value, then raise to the power this.
if it if it is 1.5, then e to the power 1.5.
You cannot write 1.5
No,
at the power.
no.
Then they will not give a question like that, I think.
Acha. Okay. Okay. But in one assignment, I have seen, I have computed one problem where there was e something power. Okay, 1.2, 1.5, like this. I have calculated.
Hmm. You
For
cannot
that,
take
I
the
have used
final
my
decimal
own
of the power.
calculator. No. After e only nothing is taken. So only
No, you
one is being.
take the value of e. Then you can write its
Yes.
power like this.
X to the power y.
That is possible then.
Hmm. Yes, 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 yes.
Okay, let's focus on this.
That.
Hmm. I mean,
Okay,
if
sir.
you
Okay,
if
sir.
you know the value of e, you put like this, then then take the power. It is possible. Then you can do it, right?
Yes, yes. Okay, sir. Thank you, sir.
So they are calling it additive attention. Okay, it's calling soft math. Let's see who is wrong, who is right. Let's clear it up. It is dot product attention. Acha. So that is called additive attention. Okay. Additive attention is soft attention. Okay. So I was using soft maths. Okay. This is the language. Let's see what is soft meaning. This is soft attention. Okay. Additive attention. Acha. So another is the long attention or multiplicative attention, which is the dot product method, which you will find in the attention is all you need paper. Okay. This is the distinction actually. So yeah, so it is not called soft math as I was saying. Okay, so it is called additive attention or soft attention. Soft attention, why? Because if you're not taking like an exact hidden state as the important one, but you're taking a combination of them. Okay, so that is why it's called soft attention. Additive, why? because additive is this mechanism. So the energy that we're learning, okay, so it is like additive in a way that concatenating the hidden state and encoder hidden state, decoder hidden states, okay, feeding through MLP to learn the alignment, okay. So this is additive nature, okay. So when we're done with the attention weights, okay, so additive attention is Bhavantan 1, okay, we got it. They are multiplied by each encoder hidden states in sum to form a context vector. That is the correct answer, right? Yeah. Okay, you can see. Yep. So news headline generator model is using additive attention at a certain at so additive attention it is using so Badana 1 at a certain decoding step the model assigns nearly equal weight to all encoder hidden states. Okay, so the following is the most likely reason. So that is the thing. All are important. That is why equal weight. In additive attention, why softmax used after computing alignment to so normalize the scores into probabilities that sum up to 1. Okay, clear, very easy. A machine translation model uses scoring function that calculates the dot product between the decoder hidden state and another each encoder hidden state to determine. Okay, so this is the next paper we have to go to. So this is a dot product based, okay, a low on attention. This paper is also there. Okay, let me open it. This is the dot product attention we have to see, but specifically like scale dot product they say. Okay. Let me take a break, okay, then we'll come back. Explain the rest of it, okay.
Yes.
Okay, so getting back to this one. So what we are having is the scaled dot product attention. So each embedding of the words are of them dimension dk. Okay, and so actually key queries and key and values are actually all the same. So dk and dv are actually also the same. Okay, may not be same when you're actually calculating interaction with the different words, then they can be different. Okay, but so key query and values, these matrices are same. So what is it? Let me explain it better. Okay, so suppose we have a sentence of like I am Anirban. Okay, super bad handwriting, but this has a embedding. This has also embedding. This has a embedding. Dimension 512. Okay, so the matrix becomes 3 into 512. Right, so this is key, query, and values. Understood? And this dk or dv are this 512 dimension. Compare the dot product of the query with all the keys. Okay, so this matrix is this dimension. So when you take dot product, what are you doing? You're taking this dot product. Okay, so this will be absorbed, right? So the final matrix will be 3 cross 3, right? So this q and k transpose is 3 cross 3. 3 is the length of the sentence. So in this case I'm considering 3 can be different as well. Okay, now they scaled by the under root dk, the square root of the dimension for stability. Okay, and the softmax is taken so that they sum up to 1. Okay, so every row sums up to 1. Okay, so like that it is taken. And now it is then multiplied with value matrix. So 3 cross 3 is then multiplied with 3 cross 512. So this becomes 3 cross 512. Clear? It is very similar to what we were doing before as well. Okay, just in dot product form. Okay, so let us understand from that context. Okay, so key and query we are having. Okay, and so you can understand it basically this way, that so query is the decoder's output, like that. Key is the encoders. Okay, so you're considering the relation between them first. Okay, and then value is the another matrix which we are considering. Okay, so it is interacting in how each words of the sentence here. Okay, corresponds to the each words of the same sentence. Actually, this is self attention and we are considering the same sentence. Okay, so this is not a translation task. Okay, it can be a translation task, but like it is the next word token prediction task. So you're given a sentence, this I am Anirban. Okay, so the model needs to given some context, it's need to produce that sentence. Okay, so it is actually the attention over the same sentence. So am is interacted with I am. So suppose here I'm considering each row is like so I am Anirban, like that. Okay, so this is the matrix 3 cross 3. Okay, these have some values. Okay, some like from 0 to 1, because why? Because softmax is applied. Okay, now so this values denotes how I interacts with the I here. Okay, how I interacts with itself. Okay, and I interacts with I am, I interacts with Anirban, like that. Okay, so those values are taken, and of course you can understand this is a symmetric matrix. Okay, so how I interacts with am here and am interacts with I, these two are same. I need to open the window. Okay, so where is it? So now the interaction is happening. Okay, now when you multiply with this matrix, which is 3 cross 5 1 2, what does it mean? There are 3 rows of 5 1 2. So I am Anirban. Okay, and each is a embedding here. Okay, dimension 5 1 2. So what we're basically doing, okay, that we're multiplying this course with these values. Okay, so we are actually learning, okay, how the attention scores corresponds to values of the embedding itself. Okay, so this, then the embeddings will change. Okay, so and that will result in the learning. Okay, how the embeddings should change according to the problem given. Okay, so we have a base case, base embedding. Okay, but then this will change. Okay, these are the attention scores. Okay, okay, so this is what we're having. Okay, so each interaction is encountered and accordingly the learning happens. Okay, they also have a multi-headed version in which the you divide the decay into suppose like 10 smaller dimensions. Okay, and then they do it. Okay, so it captures multiple context actually, so that is what it is done. So they have taken 8 as the number. Okay, so this is it, right? And this is how attention is captured. Then defined a new architecture is called transformer. Okay, so what the transformer learns is the embeddings. Okay, okay, so it gives the, so the input from the input sentence, this is a translation task. Okay, so for suppose English here, and output is Dutch, like German we are having, no? So like that, so it takes every interaction between them and updates the embedding of each word, and so these updated values are then fed to the decoder. And here first this encoder sequence happens here. Okay, and it learns the interaction between each word in German. Okay, now in the query here, so this is the query, we take the updated German sentence, German embeddings which have learned interaction between each other, and this key and value are updated English sentence which have learned the interaction between each other. Now they have to learn the interaction between German and English words. So this is called cross attention. Okay, so they do cross attention here. Okay, and update the embeddings similarly, and finally you have learned the embeddings. Okay, okay, and you calculate the softmax probabilities. Okay, so first you calculate this loss. Okay, cross entropy loss. So how is the loss calculated? The embeddings generated by the decoder model up to this stage, and the input embeddings of the what German initial embeddings were. So the loss is calculated and then back propagated. Okay, and so that is how it is happening. Okay, that is the training process. Okay, during test, during the inference, what you're having, it finally calculates the softmax. Okay, so how softmax is calculated? So the embeddings are there. Okay, now you need to calculate which embeddings deserves which probability. Okay, so it calculates that probabilities. Okay, using softmax. Okay, and then so some information is also there, I think, on that, or maybe not. And then with that probability you can do inference. Okay, so this is a more difficult paper than the previous one. Okay, so you can read this one as well, also important. So we are so this is dot product. Okay, and decoder hidden states and each encoder hidden state HI to determine alignment. What is the main advantage of this scoring method? Introduces additional training parameter for the better alignment. It is faster. There is avoiding extra parameters. Okay, the dot product, as you see, doesn't have any parameter. Is there any parameter in dot product? No. So no extra parameters were introduced. In the previous case, we were having a MLP which introduces extra parameters. Okay, that is the reason. Visible? Which of the following are valid variants of multiplicative attention
Yes, sir,
scoring?
visible.
Yes, multiplicative attention scoring. So additive was the Baden one, multiplicative is the dot product one. Okay, so dot product between ST and HI, weighted dot product using trainable matrix, weighted dot product. I've never seen this happening because it introduces extra parameters leading to slow one, but I think works out. If addition is not dot product, okay, so it's not multiplication. Cosine similarity is also cosine similarity can be calculated using dot product though.
Yeah, cosine similarity you can use, you can calculate using dot product only.
So this should be an answer, I think.
This one will be.
Because it is basically cosine similarity. We are doing u a transpose. Okay, and then we have to give it cos theta. Okay, magnitude of this divided by magnitude of this.
Mm.
So this one is like how do you write that? It is kind of like that. Okay, if I want to describe it like that, it is somehow like that. So dot product is very similar to cos theta. Okay, and all of this makes it even closer to cos theta. So I think this should be an answer. Okay. The translation model engineer switches between additive to multiplicative attention and analyzes the figure showing the dot product and distribution. So parameter. can be important. If you generate before the softmax step, then the values are going to be large. You need to have a scale like that. Okay, so that's a more difficult one. So better do it after softmax. These are the ones. Okay. This is the one, right? Easy to answer this one. Hmm. Attention helps in this. Okay. In self attention, what are the roles of query key values matrices? These are the embeddings, right? Input embeddings. Oh, acha. So better answer is that one. Attention scores calculate. We can do with query and keys. Values are combined using the weights. That's a better answer. Okay, but third answer is also not wrong though. But multiple are correct. I think this should be the answer, but I don't know. So query vector is this key vector space with dimension equal to 4 and input dot data. So input dot data first and then output dot data. But these are also dimension like this. So they are dimension like dk translate differential that multiplies this with making 4 by final root of this. Okay, q space dimension, right? And they have taken embedding as 1. Okay, but dimension taken then it is 4. So this will here in this. following real world application attention mechanisms are widely used. Neural machine translation, image captioning is also popular, speech recognition, sorting numerical arrays. Mm, Sorting you can just do it with simple sorting algorithm, I think. In image capturing mode, the attention heat map shows high heat over balls regions. So the visually the ball and the sentence in the ball corresponds well. So it is actually identifying which object is important. Okay. Why is attention particularly beneficial in long sentences? Dynamically focused. You have seen that many times actually. Now question number 30. So we are using attention. It does improve. So it's in my model interpretability. Why? Because we can see the attention scores using heat maps. Okay, that is the main benefit here. Done. Any doubt? No doubt, right?
No, no, no.
Okay. Thank you very much. So we're finished with this session.
So thank you to you
Thank
also
you, sir.
for
Thank you,
this
sir.
session.
Thank you. This is the last. Okay. To finish everything. Good luck for your results.
Yes, sir. But I have not yet got the admit card or hall ticket, as I told you.
Okay. Email them there. So
Okay.
the
So,
arena Paramita you have got.
No, sir, I also did not receive. I mailed them yesterday, but they did not reply my mail also.
Okay. See what you can do.
sir, can you please once again send the mail ID?
Yeah, I am posting here. I have.
Okay, sir.
Okay. Okay. Thank you very much.
Okay, sir. Okay, okay.
Sir, all the best for you also.
Thank you.
Like you. Have